Okay, thank you for all for coming. Today we're going to be talking about data transformation and basic data analysis. Um, Really, the goal is to take all of the data that is collected and moving forward, um, and use it. Today's agenda, we're going to introduce R for data analysis. Um, this is a pretty simple program. Once you get into it, um, then we're going to talk about data transformation, some data analysis methods, and then best practices and a checklist provided uh, for your um, for use after the webinar. So, what is R? R is an open source and best of all free statistical analysis piece of software. Um, you can add on graphical user interfaces or GUIs to make interacting with it much easier. Um, it does include basic statistical analyses tools. It allows for easy data management, so it's easier to import and transform your data. It also includes the commonly used statistical functions, frequencies, chi-square, descriptives, t-tests, things like that. It Another benefit is that it works with most common data export files. So if your data capture program exports into Excel, this R can easily accept that. If you get a SAS file or an SPSS file from an outside source, R can look into those. Um, it also allows for the saving of syntax. This will allow you to rerun analyses that need to be done in the future. So once you set it up once, you're able to quickly set it up and just save that. And then in the future, you can just rerun that syntax and not need to go through the process of resetting all that up. Some of the drawbacks is the basic program is command line driven. For those of us old enough to remember DOS and Windows and BASIC, that's kind of how it's set up. So an initial view, you're going to see basically a blank screen, and it's going to be it can be intimidating. The results view may not be intuitive. It does take a little bit of reading and kind of figuring out how it's trying to lay out uh, the formatting. And you also don't have a real-time data view, so knowing how your data is structured is important. Keep your data dictionary handy. This will definitely help as you move through and process the data. You'll be able to refer to that and understand kind of how things are going. So to install R, first you download the correct version, either Windows or Mac. It operates on both. From a CRAN repository, these are typically hosted by larger universities. They are safe, and so you can trust the downloads. The most current version of R is 4.6, titled Because It Was There. You install R just like you would any other program. In Windows, you double click and it runs the installer. We highly recommend using the default file locations just because it makes the installation much easier, and you're not trying to remember where you install things and causing problems. The next step would be install the GUI package, which is R Commander. This is done within the R program itself. If you can see right here, there's text that says install packages R Commander. You type that in and you hit enter, and then R does what you need it to do for you. Again, we recommend downloading this from a US-based mirror just to make sure that you're downloading and installing the the safe files. US based are usually at the bottom of the list, so you'll need to scroll a little bit. During the initial run, it may ask to download and install dependencies. You say yes, please say yes. This will make sure that everything that our commander needs to run is installed and downloaded as part of that process. We put kind of this screenshot up to show what the screen is going to look like, because I don't know about you, but when I do an install and I see a lot of text start popping up, I get kind of worried. It's supposed to be doing that. It'll ping the servers and downloads rather quickly. Once our commander is downloaded, you can go ahead and launch it. To launch it, it is a really simple command. Sometimes on the first run, it'll ask to install additional dependencies. Go ahead and okay that. But after all of this, after this initial setup, R really becomes a powerful tool for understanding your data and helping you process it in real time. Data analysis is easiest to analyze in wide form. If you think back to the very first webinar where we talked about data cleaning and data transformation, we did talk about wide form data. And on the screen, you'll see an example of wide form. This is where each participant is on one line and all of the variables are across. It makes it significantly easier. Most data programs will export their data in this format. Some won't. For example, the National DPP is usually in short form, and so that would need to be transformed into wide form. So once you get R up and running and have launched our commander, importing from an Excel file is really straightforward. You'd select data, import data from an Excel file, and that's it. You'll get, once you select from an Excel file, you'll move onto this screen where it will ask you to name your data set. This can be anything you want it to be. I prefer to name my data set something that's descriptive so that I know what the data is going to be when I come back to it later. You'll see that variable names in first row is checked. This is telling R that in the first row of the spreadsheet, this is where you can find the variable names. And we want to convert character data to factors. This would be if your program exports data such as male, female as M or F. It just makes sure that it's telling R that these are categorical data, and it helps R kind of understand how to deal with it. Most many programs will export missing values as blank cells. Others will do some value. Sometimes it's either a 9, Excel likes pound null. And we need to tell R what these missing values are in the data file. This is so that way when we go to analyze the data, R can look at that cell, say, nope, this is missing, and I can skip it. The values need to be consistent throughout the file. This just helps because we can't use multiple values in this area. And so doing a quick find replace in Excel, something like that, and setting them all to the same value as part of your data cleaning step will definitely help help in that area. R is case sensitive, which means that male in sentence case is not the same as male in all uppercase. So variable names, missing values, variable values need to be typed exactly as they appear in your data set anytime you're telling R to do anything. Otherwise, you'll end up with some values being transformed, whereas other values are not. The next step in importing data and getting everything ready is to look at your data and determine if anything needs to be changed or transformed. So data transformations can take raw values or raw variables, for example, a single item income measure, someone's age in years, a behavioral checklist where you have multiple variables, either yes or no, or values, or even multiple programmatic goals that can be combined into a single variable to make it easier or more meaningful to analyze. These are largely driven by the questions that you're asking. The most common transformations that I perform and that I've seen performed are to recode default values into values that are easier to work with. I use a lot of numbers when I do coding, so having categorical values as numbers makes more sense to me. You can also do simplified coding, so where a lot of data exports will do no as equaling 2 or no as equaling 9. Having no equals 0 means that that variable can be combined much easier without shifting the values. Constructed variables, these could be combining, for example, multiple programmatic goals, whether or not a person has achieved that goal, into a single variable, so that way you can know at a glance and quickly how many people have met any of your programmatic goals. We can also do age groups, so changing a participant's age in years into a categorical variable where 18 to 40 is 1, 41 to 55 is 2, changing reported income into SES groups, and again, overall programmatic goal achievement. If there's multiple program goals and you're concerned primarily with did they meet any goal of my program, this would be the one where all of those individual programmatic goals are combined into that one variable, just for ease of analysis. It's very important to document and clearly label these transformations. Any transformations that you do, that should be in your data dictionary, by including any formulas that you use, any new value labels, so that way when someone gets your data set, they can look at your data dictionary and understand how those variables were changed to create the variables that you're ultimately reporting in your reporting work. Data transformation in R is pretty straightforward. You go to the data menu, manage variables in the active data set, and you'll see a list of potential changes that you can do. The first is to recode variables. This would be where you're changing male or female into 1 and 2, or whatever values you decide, changing no's to zeros. Basically, you're changing the value of a categorical variable to better match your data analysis and the questions you're asking. You can combine variables. This will let you do mathematical operations. Think adding, subtracting, multiplication, division, creation of percents. You can also change variables from continuous to categorical. The example that I see a lot is people will use a Likert type scale in the survey, and then when they're coding that survey, they'll put the numbers instead of the text. If you bring those into R will look at those and say, hey, these are numbers. I can add them and I can subtract them. When in reality, what we're talking about is actual categories, right? So 1 is not satisfied, up to 5, highly satisfied, and doing the arithmetic transformations don't really make a lot of sense, because you can end up with a mean of 2.4, and then you're trying to figure out what that means as an interpretation. And again, anytime you change any kind of variables, you'll be doing them into new variables, and documenting it in your data dictionary will help make sure that people coming into the file know what was done and how it was done. So any data changes that we make should result in a meaningful variable or category that makes the analyses easier in the context of the questions you're asking. So always make sure that this goal is in mind when you're thinking about how to transform your data. R can also be used to create outcome variables. How the variable was created should be documented in the datasets codebook. And the formula to create that variable should also be. Here, we're creating a weight loss variable. You'll see that I'm subtracting starting weight from the final weight. I always try to make sure that my variables end up positive, so that way I'm not dealing with negative numbers. Because one of the program goals of this data set is to reduce weight. That's why I'm subtracting the final weight from the start weight. If the programmatic goal was to increase weight, this would be reversed. So my final weight would be subtracted from my start weight. Once we get all of the data transformations done and the data set has the variables and everything else that we're looking for to move into, we can start looking at the actual analysis. The data analysis should be based off of your analysis plan. We often look at what we expect to see within a data set or within a programmatic results, and we compare that what we've actually observed. So for the National DPP program, we expect to see people lose weight, and we can look at whether or not they actually did through that final weight measure. Having a written analysis plan helps really detail what questions you're asking, what your hypothesis or your prediction should be. So basically what the questions answer, what we're expecting the questions answer to be, how we're going to capture the data, what manipulations are used within both the program and within the data set, and how participants are grouped. So if they're grouped by cohort, if they're grouped by individual number of class sessions, all of these things can make a difference in our results. The data, so what are we actually measuring? So for National DPP, we measure weight, we measure time spent engaged in physical activity, we measure sometimes A1C values, and sometimes we measure class attendance. We also want to document how and if these variables should be transformed. And any assumptions that we're making within the data set. So for National DPP, we are assuming that people will exercise, that people will attend classes. One of the harder ones to get from individuals is individual A1C. And so we may decide, you know what, this is too hard. When we're dealing with participants, they may not want to disclose that. And so we're just purposely not going to measure it because we can get decent proxy measures through the values that people may be more comfortable reporting to us. Anybody that has worked with participants and gotten surveys knows that the results and the data that we collect are messy. If we have 1,000 numbers, looking at them in a spreadsheet, I know I kind of freak out a little bit and shut down and then move forward after I've calmed myself down because it's hard to understand how they all relate to each other. I know I can look at a list of starting weights and final weights, and at a glance, it'll look like someone's lost a lot of weight, but it may not be the case that they met the programmatic goal. So the data analysis really helps us combine all of the data and make meaning out of it. The two most common data analysis tools are frequencies and measures of central tendency. Frequencies tell us how often something appears in our data and how the numbers are dispersed within our data. So for example, how many men, how many women are in the data set. We can also tell what races are represented in our participant pool. And we'll know exactly how many of each reported race appears within that cohort. Measures of central tendency calculate a typical or middle number designed to describe the group as a whole. Means, this is just the arithmetic average. As we'll also get the standard deviation. This is how the scores cluster around the mean, or how the scores differ from the mean. The median, this is the middle value when we arrange all the values in a list. And the mode, which is the most frequent value. The most common form of data analysis deals with means and standard deviations. So that's kind of what we're going to focus on today. Frequencies and measures of central tendency. R can create summaries of both continuous and categorical variables. Continuous variables are things like weight, where the values could theoretically go to infinity, or age. Categorical variables are things like sex, where there's a finite number and the category name means something. Both frequencies and numerical summaries, these are descriptives. Statistics can be found under statistics summaries. Numerical summaries, you can see on the right. We can ask for the mean, the standard error of the mean, the standard deviation. These are the most common ones that people will ask for and look at. If you really want to get into the data, you can choose all of those other options, but I would really caution against it unless there's a meaningful reason that you're asking for it. Frequency distributions will tell you just count data, right? So how many men, how many women, how many white, how many black, etc. Comparative tests, This is when we're getting into the kind of the meat of the analysis. We use comparative statistics to determine the patterns we observe are happening for a reason or whether or not they're just random noise in the data or coincidental. This is where we go, this is really where we're comparing what the data is telling us with what we're expecting or what could be expected based on the outcomes that we're doing. The approach that we take depends on the questions being asked and how our variables are measured, so either categorical or continuous. Chi-square, this looks at discrete groups or categories. The example that I give in the slide deals with differences in meeting programmatic goals by gender or sex, by race. So where it's a categorical difference, right? So we would want to know potentially if men are completing the program at a higher rate than women, or if whites are completing at higher rates than other races. The results we get are the chi-square statistic and the p-value. Generally recommended rules of thumb, if p is greater than 0.05, we say that the observed and the expected counts are close, so any difference is simply due to chance. If it's less than 0.05, we can say that there's a larger gap between what we expected to see and the observed values, so the differences are notable and should be explored further. For continuous variables, age, weight, time spent exercising, rank order, or Likert type total scores, we're looking here at differences in mean. Again, we're looking at basically this results of a p-value test. Significant is less than or equal to 0.005. And what that tells us is that there's a very low likelihood that the observed differences is due to chance alone, and that there's something happening in the system or in the data set that again invites further exploration. Chi-square analysis in R, you go into the statistics menu, contingency tables. The most basic example of a chi-square is a 2x2. So whether or not a participant completed and gender, or would be the best example of a 2x2 table. We can do others, but interpretation gets complicated the more outcomes that are possible. One of the benefits of using R and R Commander is that R can either use raw data, so this is data that you've exported yourself and you have in Excel, or you can use established counts from other sources. So for example, Healthy Kids tells you that there are 500 individuals with a specific condition, and you want to know in a county, and you want to know if that is something of note. And so you can go into R Commander and use the demographics of that county that you found, as well as the counts of the number of individuals who are reporting that condition, and it will generate that chi-square table for you. It's much easier than trying to do a chi-square by hand. The formulas get kind of complicated. And so this way you can kind of analyze data that would otherwise be unique to a question that you want answered, but it's not able to be answered by the analyses provided by the primary source. So an example of a chi-square analysis, For the national DPP, we want to know if there's a significant difference in the rate of national DPP completes between individuals who self-identified as non-Hispanic and those who self-identified as Hispanic. When you select the 2x2 table, you'll get this menu. It does not matter which variable you put as a row or put as a column. Here I've selected the final ethnicity, which is a throwback to pre-fiscal year 25 DPP reporting. So this is Hispanic status, coded as 0 or 1, and final disposition, this is whether or not they've actually completed the program. Go in, click the Statistics tab, and you'll see where you can ask for row percentages, column percentages. You select for your hypothesis test, you want the chi-square test of independence. And I always ask for expected frequencies. This tells me kind of what the values should be if there is no significant relationship between completion of a program and ethnicity. It helps me kind of visualize how the test is running and the results that are going to come. Once you set this up, go ahead and click OK, and you will get the results. Results are presented in the bottom half of the R Commander screen, and it's presented as text. It's not nice formatted tables, which is, again, another drawback of R. But as long as you're paying attention to your column and row headers, it's pretty easy to figure out what's going on. So in the current example, final disposition, complete, they met all eligibility requirements. We had 304 individuals who identified as Hispanic and 189 individuals identified as not Hispanic, complete. And for those that did not complete, so there's a list of requirements, they didn't meet the necessary ones. We had 512 Hispanic individuals who identified as Hispanic, and 279 identify as non-Hispanic. Move down to the row percents. We see within each of these columns are percents, and the total will always equal 100. We then move down to the p-value to determine whether or not individuals who identified as Hispanic completed the program at a different rate, and we see that it's not significant. So we can confidently say that individuals who are Hispanic are completing, or who identified as Hispanic, are completing the program in about the same rate as individuals who identified as not Hispanic. So we don't have to worry that our program is being differentially received by individuals based on their ethnicity. If you go down to expected counts, these are the values that we're expecting to see for a non-significant results. So again, we're expecting about 313 people that identify as Hispanic to have met the eligibility requirements, and 179 who did not identify as Hispanic, and those numbers are similar to what we see in the actual observed counts. If this result had been significant, it would mean that whichever value is higher, going back to this not complete, if this p-value was less than 0.05, we can come up here and we can say, look, people that are identifying as Hispanic aren't completing the program as much as people that are. And so then that kind of flags either potential differences in the program delivery, or areas of further exploration or further concern for the program. This data set, again, it's not significant, and so we're not concerned. So the program is being received equally across our two categories, which is really what we want. Students t-test. Again, this is what we're looking at for differences in continuous variables. This is used to determine if there's a change on a continuous variable. For example, weight, Likert type satisfaction scales that we've kind of brought together across multiple potential areas of satisfaction. The numbers of minutes a person reports engaging in physical activity, anything that's continuous. So there are 3 different types of t-tests. A single sample t-test. This is testing if the sample mean is significantly different than 0. We want to know if a value for that category is significantly different than 0. If it is, then we know something's going on. A paired t-test or a repeated samples t. This is where we would compare pre-post programmatic outcomes from the same participant. What we want here is to see that this value has changed, and not only has it changed, but it's changed significantly. Independent samples t, we're comparing the means of two independent groups. Excuse me. So for example, comparing mean weight loss for men versus women. So looking a little bit more in depth at single sample t-tests, these are found under the statistics menu of R Commander. For National DPP, one of the goals is to make sure that people increase the amount of physical activity that they engage in weekly. Going back to kind of physics, it's a lot easier to get people physically active who are physically active. And so this might be a test that is run at the beginning of the program with the question that is the average number of minutes a new participant engaged in equal to 0? So I kind of get an idea of where my participants are starting out at. So the window, you pick your variable and you say that population mean is greater than mu0. This is basically saying that you want it greater than 0. If you want your population mean to be less than 0, it's that second option. And if you're not quite sure about where the population mean is going to fall, the first one means it's not equal to 0. You set your population or your expected population mean. I usually leave it at 0 for this. If you know that it should be a different number, you can put it there. 0.95 is our confidence level. With the results we get here, the p-value is less than 0. So this means that the true mean of physical activity at the beginning is greater than 0, and we get our mean, which is about 56 minutes. For repeated samples t, what we're looking at here is for a single participant, did an outcome change? So for National DPP, we're concerned with weight loss. So our first variable is the starting weight. Second variable is the final weight. Options we don't really need to concern ourselves with. You would be able to set like confidence intervals and things like that. And when we run that test, we see that the first line is telling what data was brought into the model. We see the p-value again, that is less than 0. So we know that the true mean difference between the two is not equal to 0. We accept that alternative hypothesis. We also get a sample estimate of the mean difference. So on average, participants lost about 6 pounds during the national DPP program, which is above the programmatic goal of 5. So our program is meeting that goal as at a larger level or at a higher level. Independent samples T, this is where we can go into the data and start looking at whether or not the impact of the program differs between categorical groups. I picked one where I was looking at physical activity, excuse me, to determine whether or not men reported engaging in higher levels of physical activity than women. And what we see is that, yes, again, the p-value is significant. The mean number of minutes for women reported was about 112 per week, and the mean number of minutes for men was about 137 minutes per week. So we know that men are reporting significantly more physical activity compared to, or excuse me, women are reporting significantly less physical activity compared to men. Now, because the goal isn't specific to the groups, we can kind of disregard this. Or you can go in and kind of do focus groups, things like that, to determine if differences in programming could actually increase the mean physical activity in women. Because the National DPP program has 4 or 5 different programmatic goals, it may not be important enough to further explore this. So again, this goes back to the data analysis plan in determining what further questions and what further analyses should be explored. So that is a lot of data. That is a lot of information. But once you get into it and further explore, it really does make a more meaningful impact on your data analysis, as well as your ability to shift your program to meet your participants' needs. Does anybody have, I know I kind of went through that kind of fast. Does anyone have any questions? Once we post this, there are we'll post the slides, and we do have the best practices checklist. We are providing a link to download R. This is from a trusted source. This is Iowa State's mirror of the CRAN repository. Um, the steps to install R Commander, you can just copy paste that first bullet point under 2 into R, and that will run your installation for R Commander. And again, we really do recommend selecting a US-based mirror. It's near the bottom of the list. And if you get a warning about not being able to write an initial library, go ahead and allow R to create that user-based library. To launch it, again, just copy paste this into R, and it will get, and R Commander will launch. There are some additional steps for Mac users, but I really think that most people use Windows, so we didn't go into it. If you need the assistance, I do use Mac, and so I can definitely hop on a quick call and help you with that. And then just a quick check again to import your data into R. Make sure it's clean, make sure the column formats are consistent. So date columns are all formatted as dates, numbers are all formatted as numbers. Variable names are in the first row, missing data is consistently indicated within your file. And then review the data by viewing your data frame. Other than that, thank you all for coming. I know it's a lot of information and everything else, but we are definitely able to help with some of the basics of R, and we are able to do some assistance as well. Right. Thank you all.